like that, like that, it's so nice. And she's like, okay, like this, like this.
All right, let's go ahead and get started. A few things. First off, this doesn't really affect you guys all that much because you wouldn't be here Friday anyway, but I'm not going to be here Friday. Has something come up and I won't be here. But I'm going to record either today or tomorrow and put it online so that you'll have it already. Trina's not going to be here either. Totally different situation, but she's not going to be here either. So if you have the tests, you know, the positioning test that you need to make up, if anybody in here does, and you're planning on taking it on Friday, you'll have to take it between 8 and 10. Goldie will be here in the lab, and so she can give it to you, but you need to be done by 10 o'clock so that she can get ready for lab and get it ready and get it back to you. Okay, so if you have to take the positioning test over again, just keep that in mind.
How long is how many questions is the retake?
I think it's 65.
Okay.
Yeah, it's similar to the original. So at the beginning of the semester, you know, we talked about, you know, test sequencing, and I said I was going to split up chapter 4 into two tests, and some of the information out of chapter 4 is no longer testable on the registry, or at least in the content specifications for the ASRT or ARRT. Doesn't list calculation of resistance and voltage and amperage across the circuit. So we're going to talk a little bit about it today, but we're not going to test on that because it's not supposed to not be on the registry anymore. So I'm not going to cover it as in depth as what I have in the past. And because of that, I'm not going to test on it. I'm going to explain the basics of it, but I'm not really going to test on it. So probably the most difficult portion of this chapter is I'm going to take off the test. So I'm going to take, instead of having two different tests on it, I'm going to, over this chapter, I'm going to have just one single test, and that'll be a week from Friday. So even though it's more of the chapter that we're going to test on a single test, it's the most complicated portion of the test is not going to be on the test. Does that make sense? So it's more information, but you know, easier information, I feel like. So I got a lot of editing to do to the test. So what we did on this is Wednesday, so that would have been Friday. We talked, or was it Wednesday last week? Yeah. So we talked about manipulation of electric energy to accomplish our goals, and the goal of the overall imaging system was to transfer or transform electric energy into electromagnetic energy. So we talked about where we did that. We talked about you know, the power as it's supplied to us at a very high voltage, and we have to reduce that voltage through a transformer so it can go into the hospital. We run it through a auto transformer, and we adjust the voltage in anticipation of it becoming kilovoltage in an auto transformer. It's a rheostat. We can turn it up or turn it down, but after it comes out of that, it goes into a high voltage transformer to take it from voltage to kilovoltage, right? So the auto transformer was our KVP selector, our rheostat, and its auto transformer. The high voltage transformer didn't adjust up or down, it just adjusted up in a really high magnitude, so it went from voltage to kilovoltage. At the same time, we came off the bottom of the auto transformer, just in a drawing, it could come off anywhere, really, top or bottom, but at any rate, we feed that into a filament circuit, totally different circuit, and we run it through an MA selector and then a step-down transformer, so the high voltage transformer steps up voltage. So it's a high voltage step-up transformer. Filament transformer steps down voltage, it's low voltage transformer. So, and we'll talk more about that later on. But at any rate, it comes out of both of those feed into the X-ray tube, and we get acceleration of the electrons across the tube. The higher the voltage, the faster the electrons go across the tube. hit the target, create heat. They create heat in the filament itself, deposit their heat on the anode, and some of that becomes X-rays, right? So that's your manipulation, the stages of manipulation to create electromagnetic energy out of electric energy. So we talked about what we actually create, and that's primarily heat. We utilize mechanical energy in the rotation of the anode. We create light secondary to heat, and then we create X-rays. So those are all the different types of energy that we create. We talked about electrostatics, and that was stationary electric charges. And primarily what we were interested in the discussion of electrostatics and electrodynamics is the electron, because the electron can move. Proton can't really move. If we move the proton, then we move the entire element, and we're just pushing wire at that point. We're not really doing anything with electricity. So we had three charges. We had positive charge and negative charge, and they were equal magnitude but opposite charges, right? So if we have one proton and one electron, then we have neutral charge, right? We don't have charge. And then the neutron is really a non-factor in this portion of the curriculum. Then we talked about three different ways to electrify, and we can build up electric charges by scooping them up by rubbing, and that was friction, right? When you walk across a carpet or you rub dissimilar fabrics together and you create a static electric charge. And the other two had to do with equalization and returning to a neutral state, right? So you had contact, and contact is just touching. And we kind of split hairs a little bit and talked about what induction was. And that was lightning or the discharge of electrons whenever you get close to a doorknob or cat or whatever it is that you just want to shock. So friction, contact, and induction. We talked about the earth being electric ground, which means it's essentially neutral. So there is no charge on the earth. Net charge of the universe is neutral. So the earth and the universe then becomes basically a storage place for electrons. And that's why whenever you become negatively charged, the earth is proportionally positively charged, and when you get close to the doorknob and you get that static discharge, basically the electrons going back into the earth. So we call it ground. The earth is ground. That works on two different levels. And then we had the electrostatic laws. We had four of those. Like charges do what? Repel, right? Unlike charges, attract, right? So we had attraction and repulsion was law number one. And law number two was Coulomb's law, and it really had two parts to it, and that was the electrostatic force was proportional to the number of electrostatic charges, which just meant the more electrons you have, the more force you have. So the more you have, the more you have. And the second part of that was kind of a segue into law number three, but it was basically the inverse square law. So the electrostatic force was proportional to the number of charges, but if those charges are spread out really broad, you don't really have a whole lot of force there, right? So it's inversely proportional to the square of the distance in between the charges. And the number three, the third law, was that they distribute evenly. So you put a collection of electrons on a big long wire, and they have a tendency to spread out because they're all negative charges and they're going to push each other apart. But they will concentrate on the surface with the sharpest curvature, which means you bend the wire and you kind of cram them together, and they're going to find the broadest area they're going to redistribute, right? And we'll talk about where we see that in cattle prods is what he uses. But cattle prod is nothing but a stun gun, fundamentally. All right, so electrodynamics then becomes the study of moving electric charges, where electrostatics were static electricity and stationary charges. Electrodynamics are moving charges. So now we've got charges that move through a circuit. Okay, and we are going to spend some time on the circuit, but again, in as much as the note packet had so much information on the circuit calculation of voltage and amperage and resistance throughout the circuit, we're just not going to do that. But what you have to have are fundamental particles. You have to have fundamental pieces in place for electricity to flow. Okay, so first off, you have to have a conductor. A conductor is anything that allows electrons to flow. So, the guy on the train that makes the train go is the conductor, right? So conductor is what allows the electrons to go. It's the wire that the electrons flow on. And it's usually made of metal, but there are a lot of different types of conductors as well. But for electric circuits and electricity that we can actually utilize, we're going to use metal wires. And it's usually going to be copper. Some of your older homes may have aluminum wires, but most of the time it's going to be copper. There are different conductive properties in different metals. Gold is actually a better conductor than copper. So why don't you have gold wires in your house? You couldn't afford to live in the house, right? So there are better conductors than copper, but copper is a balance between cost and efficiency and safety. All three is a very good balance. So conductor is anything that allows electrons to flow. The problem with conductors, or the problem with electricity, is that we're going to use water as an analogy for electricity because there's a lot of similarities there. Why are rivers crooked?
Erosion.
From erosion, that's one. Because they follow the path of least resistance, right? So, you pour water down a hillside and it's going to find its own path, right? But it's going to find its own path based on the path of least resistance. And electricity is going to do the same thing. So if you have conductors and you've got, let's say, I'll use a personal story. I used to live on this piece of property. It was real rocky. It was 3 acres, 3.5 acres, something like that. And the first 2 or 3 years that I lived there, I kept tearing up lawnmowers. First a riding lawnmower and then push mowers. And if you've ever mowed 3 acres with a push mower, you know you don't want to do that. But I kept tearing up lawnmowers because I'd hit rocks and I'd hit stumps and I'd hit all this kind of stuff. And after about 3 or 4 years of this and just buying lawnmower after lawnmower, I said, I'm done. So I fenced the whole thing in. Fenced the whole thing in with the exception of about a 1/4 acre out front, and I put goats out there. Anybody ever been around goats? They're really fun. Yeah, they're a very curious animal. They're a very social animal, especially if you get a male goat and you castrate them, they become like a big puppy. They just follow you around everywhere. The females are a little bit more standoffish, but the castrated males they're fun. They just follow you around everywhere. Problem is, my house, it was really an ugly house. It really was. It was basically a big long cigar box. It was 2,800 feet, and it was only about, I'd say, 30 feet wide. So it was a long, long house. But it had this patio that ran the entire length of the back of the house. And about 2/3 of that was covered. Okay, so about 1/3 of it was uncovered. So I fenced in the whole thing. It was kind of a pie-shaped piece of property, and it went like this, basically. And so I put a fence here, I put a fence here, and then, I let the goats roam all of that. They were much more efficient cleaning it up than I ever was with a lawnmower. They were awesome. I put 5 on it originally. And after about 2 months, you couldn't see through this. It was really woody, lots of vines and stuff like that. And after about 2 months, I could see from 7 feet down all the way across the property. Because they'd stand up on their back hooves and they'd eat everything, right? So they did great. but they started eating everything down. I got rid of 2 of the goats. They still were eating everything down, so I opened the back door to, or back, this portion of the property to them. So the goats come in, and again, they're extremely curious and very social. You can't have just 1 goat. You gotta have at least 2, because if you don't have more than 1, you become the second goat. They're gonna wanna be around you, okay? So, they're very social. So I got this patio, that's covered, and it's screened in, that's open. Okay, so anywhere a goat is, goat poop is, all right? So they're eating everything, and nothing's to keep them off of this, right? So they're just climbing up on the back patio, and they're pooping everywhere, and they're just making a huge mess. I gotta keep them off of it. So I don't wanna put up another fence, so I put up an electric fence. So electric fences, if you've never dealt with an electric fence, what it is basically a generator of high voltage and low amperage. So you got about 1,500 to 2,500 volts coming out of an electric fence generator. So what I did was, at the edge of the garage here, I plugged in inside the garage, I plugged in the electric fence generator, brought it around and ran a wire all the way down to here, okay? Because that was covered, right? So what you have to have for an electric circuit is a conductor, right? But the conductor has to be, I won't say pure, but it's got to not touch another conductor. All right? So looking now, we're going to change our view as if we're looking on it that way. So I've got patio, and I've got fence posts, and I've got electric fence wire. So we're going to say that's the wire. It's pull tight. I've got these posts, but the posts have to be not touching another conductor. Okay? So you got the wire, and it can't be touching anything that resembles a conductor. So what you've got are these little plastic things that the wire goes through. The plastic things keep it away from the fence posts. Okay? So the fence posts would be a conductor, but with the little plastic thing on it, it prevents the wire from touching a different conductor. So metal fence post, not good. Plastic thing keeps it off the metal fence post, and that is what you call an insulator. An insulator is the opposite of a conductor. An insulator keeps electricity from flowing. All right, so in this case, it kept the electricity from flowing into those fence posts, into the conductors that would then send the electricity into the ground, right? Because the earth is ground. So it keeps the electricity from flowing and going into the ground, and it just keeps it going. But the thing is, you have to have a complete circuit. So a circuit, in this case, it wasn't just enough to have a wire to come out. It's got to have a wire that comes out and it goes back into the electric fence generator. So it's double wire. One goes up top, one goes down bottom. So the electricity went in and it went back around, more insulators, and back into the electric fence generator to complete the circuit. Okay. Anytime you have electricity, you've got to have a complete circuit for it to flow all the way around. So the problem here, that became pretty good at keeping the goats off of the patio. The problem then became, well, that's just screen. They started butting through the screen and getting in here, and now they're right outside the house. So I had to bring it all the way down like that. So problem solved, right? For a while. So grass starts growing. Grass, you ever cut the grass? Is it just dry wood? No, it's full of water, right? So water, is it a conductor or insulator?
No.
You think so, but it's really not. And we'll get there here in a minute. It's in its natural state, it's a conductor. In its most pure state, it's not a conductor. And we'll get there here in a minute. But since it's inside the grass itself, we're going to call it a conductor. So now the grass grows up and it hits right there, and what you've got is a short circuit. So periodically, you gotta walk along, and you gotta pull up the grass or cut the grass and make sure it's not touching the wires. I'm a cheapskate, I really am. You can buy these things that test electric fence generators and whether or not you've got good conductivity, and they're like $7, you know, at Lowe's. They cost like $7. I ain't buying that, you know, because I can touch that and tell you whether or not it's working, right? So not only am I a cheapskate, I'm an idiot, right? So I walk out and I see I've got grass growing. I pull the grass up and I say, okay, it should be good. So I touch the wire, and I got nothing. Okay, I still got some grass. So I look for the grass and pull it up. I look all up and down, can't see any grass. I touch it again, still nothing. So I actually, you know, make contact with it and grab it. I can feel a slight tingle, but it's not enough to keep the goats off my patio. So I'm like, okay, I'm missing something. So I get down on my hands and knees and I start crawling around through the goat poop, crawling around looking for grass hitting the electric fence. Now, let's back up. I'm standing on my feet. There's goat poop all over this. So am I barefoot? No, I'm not. What am I most likely wearing? Boots, shoes. What are the soles of your shoes made of? Rubber. Boom. Insulated. The reason that your tools have rubber or plastic handles on them, especially your pliers and your wire cutters, is because it's very good insulated. So you don't get shocked. Ding, ding, ding. I'm not getting shocked because my boots, shoes are insulators. Now I'm on my hands and knees.
Oh.
Yeah. I got 3 points of contact on the ground, right? And I'm going along and I'm looking, and sure enough, sooner or later I bump into the fence.
It works.
It works. It worked really, really well. You know, it's funny. It's funny. My oldest son was probably 3 at this age, at this time, maybe 4. So he doesn't remember this. And he called me about, I don't know, 2 or 3 months ago. His dogs are getting out from under his fence. He said, Dad, what do I do? I said, put up an electric fence generator. He calls me back, Dad, the electric fence generator isn't working. I said, yes, it is. He said, no, it's not. I touched it. It's not working. I said, yes, it is. He said, no, it's not. I said, put your hand on the ground and touch it again. So he sets the phone down and I hear, ow! Yeah, it's working. Hilarious. You know, when you have kids, you know,
That's awesome.
y'all probably more sympathetic than I am. I thought it was hilarious. So anyway, so we have conductors. Conductors allow electrons to flow. The wire. We have insulators. So we got the wire connectors that are insulators. And then we've got what we call semiconductors. Now, I don't have anything for semiconductors here or here, but semiconductors are things that allow electrons to flow sometimes, and they allow or they disallow electrons to flow other times. Okay, so back to water. In its most pure state, if you go to the store and you look at the water section, and you've got drinking water, and then you've got distilled water. Distilled water should be just close to as pure as you can get water. Okay, yeah. So it should be pretty pure. If you were to drop 2 electrodes, and you would need electrodes, but 2 electrodes, because remember you have to have a path for the electrons to get in and to get back out. If you were to drop 2 electrodes in pure water, it's really a pretty good insulator. Okay? But where in nature do you see pure water?
Glaciers?
Glaciers? That would be as close as you would get. But there may still be some impurities. Whenever water freezes, it tends to separate out the salt from the water or any other elements. But the short answer is you don't. They tell you not to stand in water and deal with electricity because it's a conductor, but it's not really a conductor. It's a pretty good insulator until impurities are introduced. So you take distilled water and you stick your hand in it. Is it still pure?
No.
What's on your skin?
Germs.
Germs, sweat, oils, right? So you introduce, even if you had a bucket of distilled water and you were standing in it and you think, well, distilled water is a good insulator, I'm protected. No, you introduced impurities into the water that makes it a very efficient conductor. So you're gonna get blasted if you reach over and touch any kind of electric source, okay? So sometimes, in its purest state, it is a insulator, but with any kind of impurities in the water itself, it becomes a very good conductor, and therefore it is a semiconductor. We use semiconductors all the time. Your phone is full of silicone-based semiconductors. We're going to use semiconductors in the imaging system, and we'll talk about that again here in a bit. So we've got conductors, insulators. Conductors allow electrons to flow. Insulators stop electrons from flowing. They disallow electron flow. And then semiconductors can behave in either way depending on their nature. And then we've got superconductors. Superconductors are very efficient conductors, but they deserve a classification all by themselves in that they're extremely efficient. Anytime you send electrons through a conductor, what you're going to have is resistance. You're going to create a magnetic field, and you're going to have resistance. Both of those two things are going to happen. The resistance is kind of a throwback to Newtonian physics, and that is that a body in motion stays in motion, body at rest stays at rest, right? And we said that applies primarily outside of the atmosphere and gravitational pull of the Earth, out in space, right? But here, there's always that resistance, right? Resistance to change. So superconductors are extremely efficient conductors in that conductors have resistance and superconductors have less resistance. Resistance in a conductor compounds itself, okay? You ever worked on a computer in a hot room? Your electricity went out, but you've still got the battery power on the computer, and the computer gets hot. How efficient is it? What happens with it when it gets hot? It slows down. It slows down. You start having problems, right? So computers work best when they're cold, right? And that is because you're dealing with electricity, and the hotter the electricity gets, the more resistance that it becomes. It's kind of like, y'all are all young. So brothers and sisters, yeah? Mom, dad stick you in the back seat, make you sit side by side on a hot road trip. What happens? Somebody's going to get a beating, right? Okay, so same thing happens. You crowd a whole lot of electrons onto a circuit, onto a conductor, and you send them through the wire, and what you have is, because of that congestion, it gets hot, and the heat creates more resistance. Okay, so it's kind of like compound interest. One thing leads to another, and it just builds on itself, and so the resistance provides heat, provides resistance, provides heat, right? So where superconductors are is two things. One is they're really good conductors, but at the same time, they're kept extremely cold to remove some of that resistance. MRI uses superconducting magnets, and how it keeps it cold is it keeps it almost to absolute zero, which is close to 400 degrees below zero, okay? So what they use is liquid helium inside an MRI to keep the conductors so cold that they have almost no resistance, okay? So superconductors, two things about them is good conductors, but at the same time, they're kept cold to also remove some of that resistance as well, okay? All right, so when we're talking about resistance, there are a number of different things that we can do to change. We're going to just go with conductors at this point, to change the resistance in a wire. Resistance is always present, even in a superconductor. It's just that it's extremely low, but it's still there. So how we can deal with resistance in a conductor is to do a number of things. All right, so again, back to water. I have just a pipe that's this big. Okay? And I compare that to a pipe, here, I need another tubular shaped thing. Let's say I was gonna fill this bucket with water, and I had a pipe the size of this thing, okay? And I had another pipe the size of the end of this femur. So the wall of the pipe's the same size, the diameter, the inside diameter or lumen of the pipe is different size. So which one's bigger?
The femur.
The femur, right. So if I had a pipe, same water pressure, and I were to try to fill that bucket with this versus this, which one's gonna fill faster?
Femur.
Femur, right. So the bigger pipe is gonna fill faster, because the smaller pipe is gonna have more resistance. The water, you're gonna have a harder time pushing water into the smaller pipe in order to get the same amount of water out quickly, right? So, in resistance, if we're using water as an analogy, then what we're looking at in a conductor is basically a pipe. So we've got a wire, and we're gonna call it a pipe, but instead of having a hollow inside, we're gonna have electrons on the outside, okay? So if you have a wire that's that big, and then you have a wire that's that big, how many electrons can you put on each one proportionally? More here or more here?
More and bigger.
Significantly more over here, right? So bigger wire, less resistance. Bigger wire, you can push more electrons through the wire at any given time, okay? So resistance can be changed by changing the diameter of the wire. Okay, so bigger wire, less resistance, more electrons can flow. That's number one. Number two is the length of the conductor. And this is a little bit harder to wrap your mind around, but it kind of makes sense at the same time. It's harder to illustrate, really. If you have two pipes, again, one is only that long and one is extremely long, then as the water flows through the pipe, the resistance is going to be at the surface right here. So what you're going to have is kind of like in a river. You've stood by a flowing stream and you've seen the water going down the middle of the stream, and it flows pretty unencumbered. But at the banks, it kind of has a tendency to swirl, right? And slow down at the banks as it's dragging along the solid matter at the banks. It's what you call eddy current. So in the water, what you're going to have is eddy current for the entire length of whatever pipe you're going to send the water through. Okay? So if all of that eddy current provides resistance, then which one of these two pipes is going to have the most resistance? The longer one, right. So diameter of the pipe, or diameter of the wire, length of the wire, and then finally, the third thing would be the temperature. Because again, if we keep a superconductor very, very cold, then it becomes, or if we keep a conductor very, very cold, it becomes more like a superconductor, okay? So change the temperature of the wire, change the diameter of the wire, change the length of the wire. Are the three different ways we can change resistance. Now what we can also do is two different things. One is we can add a resistor, all right? So that sounds kind of like double talk. To change resistance, we add a resistor. And in this context, we're not just talking about the resistance in the wire, but we're talking about something that you put into the system that introduces resistance. So now we got all this electricity flowing, and we've got a relatively broad wire. Let's say our wire is that big, and we feed it into a light bulb. And what does a filament in a light bulb look like? It's swirly. So is it like this or is it like that? Well, you take that and you double it up, and it looks a lot shorter, but is it? No. Okay, so it's a relatively long wire made to look short. right? So that's number one. And number two, would that filament be as broad as this wire is up here? No. So what you've got is a little bitty skinny wire that's a long wire that's curled up, okay? So a resistor is anything that's placed into a circuit that provides resistance, okay? And the resistance it provides is not necessarily wanted, but it uses the electricity and therefore provides resistance to more flow of electricity. The light bulb uses up some of that electricity, it glows, okay? As long as there's still a constant flow of electricity through there because that's not broken, then the electricity continues to flow, it's just that some of it goes through there. All right, make sense? So a resistor is anything that you put inside of the electric system to create resistance, or anything that you're using that the electric system uses for your benefit is a resistor. Okay? So adding a resistor, changing the diameter of the wire, changing the length of the wire, changing the temperature of the wire. And finally, you can manipulate your electric flow using what we call Ohm's law. Okay, so Ohm's law. Where's Ohm's law? Ohm's law is on page 67. So voltage is equal to I is amperage. Okay, amperage is intensity. That's why we say when we're controlling an X-ray beam that if we want to change intensity, we change amperage. Amperage equals intensity. So Ohm's law says V equals IR. R is resistance. So let's say, again, I like to simplify formulas just for demonstration purposes. So if we have 1 volt and 1 amp, then our resistance has to be, to make this, yeah, to make that mathematically correct, is 1. Now, what if I cut my resistance, or maybe I double my resistance? Now what happened?
It's not true.
Hmm?
It's not true anymore.
It's not true anymore. So 1 times 2 now becomes 2, right? Now, what we can use in order to make electric flow a lot more efficient is this. What if we were to utilize a much smaller wire, which would increase our resistance, right? We increase our resistance, then in order to get those electrons through that wire, then what has to happen? We increased our resistance, and what went up? Voltage, right. So thinking about the electricity that comes to your house, and thinking about the electricity that goes to all the houses, you know, those big wires that are relatively large, right? Some of them are quite big, some of them not so big. But in order for the electric power to reach all the houses in your neighborhood, can you imagine if every house in the neighborhood was bleeding off a little bit of that electricity all at the same time, how much electricity and how many electrons would have to flow through that great big wire? So in order to get all that electricity, what we would have to have is a massive wire that the telephone poles could not hold up, essentially. So what we can do, the reason electricity comes to you in very high voltage is because it's more efficient to send 400, say 450, maybe 500,000 volts at very low amperage down the electric wires than to send, you know, you might use 110 volts, 120 volts in your house. So if we can substitute voltage for amperage, then essentially what we can do is we can use a smaller wire with lower resistance, or rather, it's going to have higher resistance, but using higher voltage and lower amperage to deliver that same amount of power. Because electric power is equal to voltage times intensity. Okay? So, voltage times intensity, again, we've got 1 equals 1 times 1, and if we double our voltage, what can we do with our amperage?
Half it, yeah.
Half it, right? So if we increase our voltage by a factor of 500 times, let's make it easy. Let's say 1,000 times, then our amperage naturally is going to be 0.001, right? So we can trade off very high voltage for very low amperage. The reason that we have such high voltage coming from the power company is for that purpose. So we can use a very small, relatively small, much smaller wire with higher resistance to send the same electricity to your house. Now, you start trying to use your oven with 500,000 volts, what's going to happen? It's going to fry it, right? So it's got to go through the transformation process and the transformer out, on your telephone pole in order to make this into a usable amount of electricity voltage. All right? So we can manipulate voltage and amperage, and they're directly or inversely proportional. As voltage goes up, amperage goes down. As amperage goes up, voltage goes down. We can use that, according to Ohm's law, in order to manipulate resistance and utilize smaller wires and resistors to accomplish the same thing, higher voltage. Okay? Now, we've got two different types of circuits. And again, we're not going to calculate the voltage and resistance across each one of these, but we've got two different types of circuits and we use both types. Now we've got series circuit. What's a series? Just definition of a series. Multiple things, right? So multiple things of similar type or identical type. In the baseball season, what's the championship? What do they call it? World Series, right? So can you get to game 3 before you play game 1? No. So there are multiple things of similar type that have to be performed in sequence. All right. So just a simple drawing of a series circuit would be where we've got, as supposed to be a resistor, could be a light bulb, doesn't really matter. And then the electricity has to flow from one to the other. So we've got flow of electricity that goes, let's say it's direct current, it's coming from a battery. And let's see, battery, that's ground. So we've got a battery flow of electrons from out of the battery through a resistor. It's got to come out of that resistor to go into the next resistor. Now backing up, your batteries, the terminals seem to be opposite from what we're talking about in flow of electrons. So flow of electrons flow of negative charges, right? Batteries are a little bit confusing electric circuits are a little bit confusing in that the positive side is where the flow of electricity comes from. And the reason it was like that is because whenever they were first learning about electricity, they didn't really know what electricity was and they thought it was positive charges. We've since learned that they're actually negative charges, but the labeling just never made that change. Okay, so we're going to think of it as the positive flow of negative charges. Okay, so we've got flow of electrons, and in a series circuit, it's got to go through one to get to the next. In the X-ray circuit, where we see that is the first thing it gets into is what? That thing? Auto transformer. There you go. Auto transformer is a type of rheostat, and its purpose is for KVP selection, right? So it's KVP selector. After it comes out of that, what does it go into? High voltage transformer, exactly. High voltage transformer has more turns on the
On the primary.
secondary side than what it has on the primary side, right? So can our electricity get to the high voltage transformer before it goes through the auto transformer? No, series circuit. So after it comes out of that, what does it go into?
To the,
Into the X-ray tube, right? So series circuit, you gotta go through one thing to get to the next. You can't get to the X-ray tube until it goes through the high voltage transformer. You can't go through the high voltage transformer until it gets to the, until it's been through the auto transformer. At the same time, we've got another circuit that comes off, and we call that the low voltage or filament circuit. In the low voltage circuit, we've got more turns on the primary side than what we have on the secondary side, okay? So this right here is your MA selector, okay? So that's your MA selector. Can you get to the low voltage transformer before you get to the MA selector? No, so series circuit, it's still connected in series. Then it comes out of that and it goes into the X-ray tube. So you got series, but at the same time, what we've got are two separate circuits, and those circuits are going like this, okay? So if we take two things and we run them side by side and they never touch, just like L's, right? You got L's and they're right next to each other, then they're not touching, right? So what do we call that relationship? Parallel. 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 So what we've got are two different circuits that are series circuits that are parallel to each other. Okay, so we got series circuit, and those two are parallel to each other. Okay, so we got different different types of circuits that we're going to use. The benefit to the series circuit, really not benefit, but you know, we couldn't, in the X-ray imaging system, we couldn't perform what we need to perform with voltage manipulation without them connected in series, right? And at the same time, we couldn't simultaneously have high voltage and low voltage exist in this circuit without having them hooked up in parallel. You see both of these in your house as well. All right, so let's say you plug in something in your kitchen. I got a problem in my kitchen. You plug into just the right plug, and all the plugs in the kitchen go dead. You seen something like that before? Okay, you blow this one here, then how is electricity going to get from here to there? It can't, right? So Christmas time, you got a string of lights, right? And one light bulb burns out, and the whole string of lights go out. That's what you're looking at. Series circuit, this one blows. Electricity is going here, and what you're doing is you're bleeding off a little bit of electricity there, but it continues on. You bleed a little off there, but it continues on. So in a series circuit, or a parallel circuit rather, if that particular thing blows, can that still work? Yeah, absolutely it can. Right? So you've got Christmas trees that on the box it says stay lit. Have y'all ever seen that? Been shopping for a Christmas tree or anything like that? At some point you will. And make sure that if it's a pre-lit Christmas tree, it says stay lit. Because what that means is your light bulbs are connected in parallel, so that if it's not a stay lit and you burn out one light bulb, you don't have a lit Christmas tree anymore, right? So that's a parallel circuit. So how many filaments do you have in an X-ray tube? How do you control your focal spot? Hello? Huh? Not the mirror. Not the collimator. Your focal spot is where you actually make the X-rays on the face of the anode. Okay, so what you've got, blown up view of the inside of the X-ray tube, so this is the anode. And what you've got is a filament, and the filament provides electrons to go across and create your X-rays right there, right? So the focal spot is the actual area of bombardment on the face of the anode. That's where the electrons strike. And you can change that because you've got two different filaments. On your control panel, when you go back into clinicals tomorrow, take a look, you should have two buttons. One button that looks like that, and one button that has a square inside of a square, okay? And what those are is filament selectors. So that if you want an image with a lot of detail, like if you're shooting hand x-rays and you want to see the trabecular markings in the hands, then what you want to select is a small focal spot size. So that would be that. If you're taking a x-ray on an abdomen, you know, how much detail do you see on a KUB? You know, it's all soft tissue. You really can't see any detail. Do you need to put all these electrons on that little bitty filament? No. So you use a bigger filament, right? Now here's the thing. If one of those blows, you know, small filament, you make a mistake and you've been shooting KUBs on a large filament for, 6 months and you just blow your small filament, you can still use your large filament because they are connected parallel, right? You blow your auto transformer and guess what? No more, you're dead in the water, right? Your entire system is gone. Okay, so parallel, series circuits, we use both of them. Any questions on those? So electric power, you take a light bulb out of it's burnt out, and you take it out, and you look on the end of it, and what do you read? 60 watts, right? 60 watts. Measure of electric power is wattage. And it's just a multiplication of your intensity and amperage and your voltage. So in our, where we see that in the imaging system is that our transformers are going to be rated according to their wattage. So let's say you go into a dentist's office. Their transformers, the transformers in their dental units are going to be rated at a much lower wattage value than what ours are in diagnostic. Mammography, just shoot through soft tissue, lower wattage value than diagnostic. Therapy uses megavoltage. So very much higher wattage value than ours. Okay, so wattage is just a measure of electric power. Voltage is basically the engine that pushes these things along. And because of, anybody pick up the DeAngelis book, or not DeAngelis, the Carlton book, The Art and Science of Medical Imaging. It was that optional book that we told you about. You got it? Okay, so if you read through his book, he goes into, at least last time I read his book, he goes into great detail in trying to describe these two things. So, he tries to tell you that actual flow of electrons is inversely proportional to traditional flow, and that's basically what I explained in this. But in the difference between perspectives, what you'll have is some people will say that voltage is actually a pulling force. So that voltage really is as if you applied the voltage over here. So you got a flow of electrons. Electrons are all negative charges, right? So you got a flow of negative charges. So what you have is positive charge being the voltage that's pulling these things along. We're not going to focus on that. We're going to focus on the electrons, the voltage being the thing that pushes the electrons along. you supply electrons, and what you've got is a repulsion type of interaction, because you're supplying electrons to electrons, the like charges repel, right? So when we get to travel of electrons across the tube, what we're going to say is we apply the KVP over here, and the electrons jump across the tube. Okay? I don't want you to get all tied up into where the KVP is applied. You know, some people in the hospital say, well, KVP is applied over here. Now, that's all well and good in this perspective. You can take if you want to, but logically, in my mind, you're going to have to come up with an explanation of where the positive charge comes from. Where do you get a positive charge? Did you supply a whole lot of protons over here to draw them across? Well, no, the protons were already there in the circuit, you know. So I just point that out because somebody invariably comes to me and says, so-and-so in the hospital says that we apply KVP to the anode end of the X-ray tube. Whatever. Does it matter? No, it doesn't. Is it going to be on the registry? No, it doesn't. So we're going to keep this perspective and just deal with it. Okay? Any questions? We only got about 10 minutes left, and next step is to get into magnetism, which is kind of taking a little bit of a different direction. So I think we'll pull up there. Any questions?
Can you repeat what will not be on the exam anymore?
Yeah. Okay, so, and some of y'all might want to take a look at this. So I've actually taken the pages out of the previous DeAngelis, and I've scanned them in, and I'll put them into Canvas so that you can have the pages that shows how these things work. But you see where on page 68, you've got calculation of resistance, intensity, and voltage through both of these types of circuits. We used to have to do that. So what we would do is, you know, a series circuit is provided with 110 kVp, and we've got resistance R1, R2, R3. Resistance is, you know, 5 ohms, and we'll have to calculate intensity, you know, the amperage on each one of those. And I looked at the content specs this morning, it's not on there. So, you know, we're gonna focus on something.
So no math on this test?
No math? No math? No, there's gonna be math, but this is not gonna be it. Yeah. Good try.
I tried.
You tried. But we are gonna talk about the manipulation of KVP and that math, and the transformer laws will be on it.
No calculation for circuits.
No calculation for circuits, right? And then in your note packet, there's probably 2 or 3 pages dedicated to that.
Okay.
So, any questions? All right. Then again, I will record Friday's lecture and I'll put it online.